everyone. So today, we've got this really cool story for you. It's about how a clever, old trick from the very beginning of classical computing is actually helping to solve one of the biggest problems for quantum computers.
Okay, so let's just dive right in. We hear it all the time, right? Quantum computers are the future. They're going to solve problems we can't even dream of with today's machines. But if they're so powerful, what's the holdup? Why aren't they everywhere yet? Well, as it turns out, a huge piece of the answer comes down to one thing: cost.
And that gets us right to the heart of what's known as the quantum cost problem. To really get it, we need to pop the hood and look at the basic building blocks of any quantum program, these things called gates. And as you're about to see, not all gates are created equal, not by a long shot.
So, picture this. Quantum programs are basically built with two kinds of tools. On one side, you've got your Clifford gates. Think of these as the simple, reliable workhorses. They're fast, they're cheap, they're easy to work with. But on the other side, you've got the T-gates. Now, these are the superstars. They're incredibly powerful, but they are also incredibly expensive, really complex, and just a huge pain to protect from errors.
So the obvious question is, well, why not just get rid of the expensive T-gates? Just use the cheap ones. But here's the catch. You absolutely need them. Without T-gates, a quantum computer has no real advantage over the laptop you're probably watching this on. They are the special sauce, the key ingredient that gives quantum computers their power.
And this is really the whole point. Since these T-gates are both essential and expensive, the name of the game in quantum programming becomes incredibly simple. Use as few of them as you possibly can. This leads to this critical measurement called the T-count, which is literally just the number of T-gates you have. That T-count is our main measure of cost, and the goal is to drive that number down, down, down.
All right, so the problem is clear. Our T-counts are too high, making things too expensive. So how do we fix it? Well, this is where the first really big breakthrough happens, where researchers took this very physical, very real-world engineering problem and turned it into a problem of pure mathematics.
What they figured out is that you can describe any quantum circuit, I mean any of them, with a special kind of mathematical formula. It's called a phase polynomial. You can kind of think of it like translating the super complex architectural blueprint for a skyscraper into one single clean, elegant equation that captures everything about its design.
And here's where it gets really, really cool. This formula has a secret hidden inside of it. It doesn't just describe what the circuit does, it holds the key to how much it costs. It turns out that the T-count, that big, expensive number we want to shrink, is exactly the same as the number of odd-numbered terms in the formula. Just like that, our tricky engineering problem becomes a math puzzle. How do we get rid of the odd numbers? This opens the door for an amazing trick. It turns out there are these other special, invisible formulas you can add in, and it's like a mathematical magic trick. You add them to the main formula, the coefficients change, odd ones can flip to even ones, but the final answer that the circuit spits out stays exactly the same. It means we could create a totally new, much cheaper circuit that does the exact same job. I mean, this just completely changes the game, right? The new mission isn't about rewiring circuits. It's about finding the perfect invisible formula to add to our equation. And that search, well, it leads us somewhere totally unexpected. A rescue mission from the world of classical computing. So, where would you even look for something like this? A whole collection of these perfect mathematical objects. You'd think the answer would be in some brand new quantum physics paper, right? Nope. The answer was hiding in plain sight, in a field that's been around since the 1950s.
The solution was just sitting there, in classical error-correcting codes, specifically something called Reed-Muller codes. Yeah, this is the stuff that was designed decades ago to stop the static on your radio or fix an error on a scratched CD. It's just wild to think that the math behind that old problem was the perfect key for this very new one. And this table just lays it out so perfectly. This isn't just some loose comparison, it's a direct one-to-one translation. The quantum circuit's formula, that's like a message that got scrambled with errors. That set of invisible polynomials we're looking for, that's the Reed-Muller codebook itself. And our quantum goal of finding the cheapest circuit, it's the exact same problem as the classic task of decoding the message. So the whole optimization process becomes this beautiful, surprisingly straightforward recipe. Step 1, translate your quantum circuit into its formula. Step 2, pretend that formula is a garbled message that needs decoding. Step 3, you run it through a classic Reed-Muller decoder to find the closest clean message. And voila! Step 4, the result is a brand new formula for a much, much cheaper quantum circuit that still does the exact same thing.
Okay, so the idea is super elegant. It's a beautiful connection. But, the big question is always, does it actually work in practice? Does it pay off? Well, let's look at the results because they are genuinely impressive.
So, how well did it do? On average, this technique chopped the T count down by about 6% compared to the best methods we had before. Now, you might hear 6% and think, that's not a revolution. But in the quantum world, where every single gate is incredibly precious and expensive, saving 6% is a really, really big deal. But that was just the average. It gets even better. For some specific, really important circuits, the improvement was just staggering. This method was able to slash the T count by as much as 75%. That's not a small step. That is a gigantic leap forward in efficiency.
And beyond these practical wins, this work revealed something truly profound about the problem itself. It proved that finding the absolute most optimized perfect circuit is exactly as hard as that classic problem of decoding these old codes. Now that tells us a perfect solution is probably out of reach because it's a fundamentally hard problem. But, and this is the exciting part, it also gives us a clear roadmap. Anytime someone gets better at classical decoding, we automatically get better at building quantum computers.
So, let's just step back for a second and see why all of this really matters. First, it gives us this single, unified mathematical way of thinking about quantum optimization. Second, this isn't just a one-trick pony for T-gates. The same idea can be used for other expensive quantum operations too. And, maybe the most important part, it lets us take all this brilliant research from the last 70 years of classical computing and plug it directly into building the better quantum computers of tomorrow.
And it all just leaves you with this really fascinating thought, doesn't it? That sometimes the key to unlocking the technology of the future is actually hidden in these brilliant ideas from the past. It makes you wonder, what other secrets are just out there waiting to be rediscovered? Thanks for joining me.